This lecture is about norms. We'll look at some you've probably seen before and some you probably haven't. A norm is a way of measuring the length of a vector. In particular, it's a mapping from our vector space Rn to R, and it must satisfy some properties that make it behave the way we expect a length measurement to behave. These properties are: 1. The norm of a vector must always be non-negative. You can't have a length be a negative number. And if your vector is 0, then your length must be 0. And if your length is 0, then your vector must be 0. 2. The norm of a sum must be less than or equal to the sum of the norms. This is called the triangle inequality, and it's based on the following picture. If I have a path, x plus y, then the length of that path must be less than or equal to the sum of the lengths of the paths x and y. 3. If I scale a vector x by alpha, then I scale its length by the absolute value of alpha. Let's look at our first example of a norm, the 2 norm. This is the familiar Euclidean norm, where in order to measure the length of a vector, I take the square root of the sum of the squares of the components. In my opinion, the best way to visualize a norm, if you can, is to draw all the points in our vector space that have norm 1. In this case, here's the origin, and all of the points on this circle right here are the points that have norm 1 in the Euclidean norm. It's worth noting as well that this norm arises from the inner product that we've already discussed. Our next example of a norm is the 1 norm. This is also called the taxicab norm for reasons I'll explain in a moment. To compute this norm, we sum up the absolute values of the components of the vector. So again, let's visualize the norm by drawing all the points in our vector space that have norm 1. Here's the origin. All the points that have norm 1 give this diamond shape. How does this norm measure distance? Well, if this is the origin, and I choose a vector whose tip is, say, right there, in order to measure the length of this vector, I have to measure the x1 component and the x2 component and add the two together. So this is actually why it's called the taxicab norm. It's the same way you'd measure distance if you were driving in a car or a taxicab along the city streets. It's also worth noting that this norm does not arise from an inner product, like the 2 norm did. It's a little tricky to see why this is true, but a typical strategy would be to try to verify that an identity that holds for norms that come from inner products does not hold for this norm. One such identity is the parallelogram law. Any norm must satisfy the 3 properties of a norm that I listed earlier. Let's verify property 2 for the 1 norm. Property 2 is the triangle inequality. It says that the norm of a sum must be less than or equal to the sum of the norms. To do this, we'll rely on a simpler fact, which is, well, the triangle inequality for the absolute value. So let's see how this works. The 1 norm of x plus y, by definition, is the sum of the absolute values of the components. Now, the triangle inequality for the absolute value says that the absolute value xi plus yi is less than or equal to absolute value xi plus absolute value yi. So by replacing each one of these with this, we get a less than or equal to in the sum. Now, let's split up the 2 terms of the sum here into the sum of absolute value xi and the sum of absolute value yi, which are, by definition, the 1 norm of x plus the 1 norm of y. Let's look at another example of a vector norm. This is called the infinity norm, or for obvious reasons, also the maximum norm. So the infinity norm of x is the maximum of the absolute values of the components. Again, let's visualize this norm by drawing all the points in the vector space R2 that have norm 1. Okay, so here's the origin. Put the tip of a vector, say, right here. When would this vector have norm 1? Well, precisely when one of the components has absolute value 1 and the other component has absolute value less than or equal to 1. So, for example, right here, the component in the x1 has absolute value 1 and the component x2 has absolute value less than or equal to 1. Etc. Finally, I'll point out once again that this norm does not arise from an inner product like the 2 norm did. Let's finish our discussion of vector norms with a family of examples called p-norms, and these are defined for p greater than or equal to 1. The p-norm is defined as the pth root of the sum of the pth powers of the absolute values of the components of the vector. Our previous examples were all p-norms. The first example was for p equals 2. The second was for p equals 1, and the third was for p equals infinity, even though it may take a minute to see why p equals infinity would give the maximum of the components. Now, by no means are p-norms the whole story. There are lots and lots of other norms that we can put on Rn. So for example, if A is an invertible matrix and this guy right here is any norm at all, then we can define a new norm, which we'll call norm sub a, by taking the old norm of ax. That defines a norm. So we can get lots and lots of norms. We can also mix and match bits of the norms that we've seen so far. So for example, we could do this so-called weird norm, where I'm going to take the absolute value of the first one, then I'm going to take the square root of the square of the second plus the square of the max of the third and the fourth. Okay, that's a weird one. I don't know why we would use a norm like that. We're going to stick mostly to 1, 2, and infinity norms for a lot of our examples. We've talked about vector norms. Now let's talk about matrix norms. In particular, matrix norms induced by vector norms. So as usual, let's let A be an m by n matrix, and I think of A as a mapping from Rn to Rm. To define the matrix norm induced by vector norms, I have to choose norms on the domain Rn and the codomain Rm. In general, these could be different norms, but let's assume that we have the same norm. So for example, on Rn and Rm, we choose the 2 norm, or on both Rn and Rm, we choose the 1 norm. So these norms on Rn and Rm induce a norm on A. And essentially, what this norm captures is exactly how much A will amplify the length of a vector in the chosen vector norms. Let's see if we can parse the definition of an induced matrix norm, norm A. I'm going to give 3 equivalent definitions, which are pretty closely related, but I'll start with the definition that I think is the clearest and the easiest to understand. So I have a choice of norm on Rn and Rm. I'm going to define the induced matrix norm, norm of A, to be the maximum of norm of Ax over all choices of x with norm 1. So, in other words, I choose an x with norm 1 in Rn, I compute Ax, and then I compute the norm of Ax in Rm. That essentially tells me how much A amplifies that vector x with norm 1. I then take the maximum over all possible choices of x with norm x equals 1, and so that tells me the maximum amount that A can amplify a vector with norm 1. There are 2 other equivalent definitions that I'll briefly explain. So I could also take this second definition where I maximize, again, the norm of Ax over choices of x. But this time, my choices of x are going to be any x at all that's non-zero in Rn, not just the ones with norm 1. But to account for amplification that happens in the choice of x, I'm going to divide out by norm of x. This will give me the exact same result as the above. Finally, a third definition, which is almost exactly the same as the second, is to look for the smallest c so that the size of the norm of Ax is bounded by c times norm x. A way to see that this is essentially equivalent to the second is divide both sides of this by norm x, and you'll see that essentially finding the maximum of norm Ax over norm x is the same thing as finding the minimum value that bounds it above. I think you'll agree we really need some examples. Let's start with this matrix A, which is a mapping from R2 to R2. I'm going to choose the 1 norm on R2 to induce the 1 norm of the matrix A. So, by definition, the 1 norm of the matrix A is going to be the largest 1 norm of Ax, where the input x is chosen with norm 1. A really nice way to visualize this is to take all of the vectors x with norm 1 and then to hit them all with A. If I hit all those vectors with A, I get this shape right here. So what we are looking for then is the point on this shape that has the largest 1 norm. It happens that the points on this shape with the largest 1 norms are 3, 2, and -3, -2. So the largest 1 norm that we can obtain out of Ax with an x chosen to have norm 1 is the norm of 3, 2 or -3, 2. That norm is 5. So we have found that the 1 norm of the matrix A is 5. Let's do the same thing for the matrix norm induced by the infinity norm. We'll choose the same matrix A, and this time we'll choose the infinity norm on R2 to compute the norm of A in the infinity norm. Again, the infinity norm of A is going to be the largest infinity norm of Ax that we can find for an input x that has infinity norm 1. Visually, we'll go down here and we'll select all the points that have infinity norm 1. These are our x's. We hit all these x's with A and we get this shape. So what we are looking for now is the point on this shape or the points on this shape with the largest infinity norm. It happens that the points 4, 2, and -4, -2 are the points with largest infinity norm. The infinity norm of these points is 4, so the infinity norm of A is 4. Finally, let's look at an example of the matrix norm induced by the vector 2 norm. We'll choose the same matrix A, and we will attempt to compute the 2 norm of A. You may have been lulled into believing that computing induced matrix norms is not such a hard thing from the previous 2 examples. But for the vector 2 norm, computing the induced matrix norm is actually a fundamental computational problem. As before, we'll choose all the points x here in R2 that have 2 norm 1. We'll hit all these points with A, and we get this ellipse. Now, we look for the points on this ellipse that have the largest 2 norm. Evidently, it's these endpoints at the ends of this major axis, but it's hard to know exactly what those endpoints are. We can sort of estimate them. It looks like roughly this endpoint would be 3.1, 2.0. So we can compute the norm of that point, and we get approximately 3.69 for our matrix norm. Actually, this visual estimate is not too bad. If we use the MATLAB command norm of A2, we get the more precise answer of 3.7025. Either way, I hope you get the sense that computing the matrix norm induced by the 2 norm is a fundamentally different problem from computing the matrix norms induced by the 1 norm or the infinity norm. Okay, to wrap up our discussion of matrix norms, I'd like to back up my vague claim that computing 1 norms or infinity norms of matrices is actually easier than computing 2 norms. So what I'd like to do is prove a theorem about how to compute the 1 norm of a matrix. If we take a matrix A with columns A1 through AN, then the 1 norm of A has this very simple formula. I compute the 1 norms of the columns, and then I take the maximum over all of those 1 norms. And that is the 1 norm of the matrix A. I like the proof of this theorem for a couple of reasons. One reason is that it uses properties of norms in an essential way. Another reason is that the strategy of proof that I'm going to use illustrates an idea and a strategy that we will see several more times as these lectures continue. Okay, let's do it. Let's choose a vector x in Rn that has 1 norm 1. I'm going to hit that vector with A, and I'm going to look at the 1 norm of Ax. By definition of matrix multiplication, Ax is the linear combination of the columns of A with coefficients xj from x. So the 1 norm of Ax is the 1 norm of this linear combination of the columns of A. Now, by the triangle inequality, the norm of the sum is less than or equal to the sum of the norms. That's our second step. Okay, now let's apply property 3 of the norm, and this is a scalar multiplying the vector aj. So I can take that scalar out and replace it with the absolute value of the scalar by property 3 of norms. Okay, let's continue. First, a quick side observation. If I take a column of A and I take its 1 norm, that, of course, must be less than or equal to the maximum over all the 1 norms of the columns of A. So, if I start with the sum that we ended with on the previous slide, and I replace the norm of each column, aj, with the maximum over the norms of all columns, I get a sum which is greater than or equal to the original sum. This quantity right here does not depend on j, so it can be factored out of the entire sum. So I end up with the maximum over all the 1 norms of the columns of A times the sum of the absolute values of the components of x. Now, hopefully you recognize the sum of the absolute values of the components of x. That's just the 1 norm of x. Now, the 1 norm of x is 1. X was chosen as such. So, this whole quantity simplifies just the maximum over the 1 norms of the columns of A. So, we have established that for any choice of x with the 1 norm of x equal to 1, the 1 norm of Ax must be less than or equal to the maximum of the 1 norms of the columns of A. Now, the 1 norm of A is the maximum over all of these 1 norms of Ax with a choice of x with 1 norm 1. So, since all of those choices are bounded above by the maximum of the 1 norms of the columns of A, the 1 norm of A is also bounded above by the 1 norms of the columns of A. Okay, cool. So we have bounded the 1 norm of A. We've shown that it's less than or equal to the maximum of the column norms of A. But the original theorem was an equality. In order to show that we have an equality, we need to achieve that bound. In other words, we need to find some particular vector x star so that the one norm of ax star is equal to the maximum of the column norms of A. That will show that this less than or equal to is actually an equals. Let me describe how we'll achieve this bound. Let's look at the maximum over the norms of the columns of A. This maximum must be achieved at some particular index, let's call it k star, so that the norm of ak star is equal to the maximum over the norms of ak. Let ek star be the vector in Rn that has a 1 in the k star component and a 0 everywhere else. It is worth noting that this ek star has a 1 norm of 1, and it picks off the k star column of A. This will be exactly the vector x that we plug in to achieve the max. So we have a ek star in one norm is equal to the one norm of ak star, which, as before, is equal to the maximum over the one norms of the columns of A. So, by choosing x equals ek star, we find that the one norm of ax is as big as it can be. That shows that the one norm of A is actually equal to this quantity, the maximum over the norms of the columns of A. Now, this proof illustrates a very important idea that we will see again and again. If we want to find the maximum or the minimum of a given quantity, one great strategy is to bound that quantity and then to show that we can achieve the bound. We will see this idea again very soon. This isn't quite what I meant by very soon, but I'd like to show you a very similar theorem for evaluating the infinity norm of a matrix. So if I take the rows of A instead of the columns, I denote them by A1 bar through AM bar, then the infinity norm of A is the maximum over the one norms of the rows of A. And yes, that is the one norm, not a typo. Now the proof of this result is very similar to the one we just did, and I'll leave it up to you.